Alrighty, welcome back after lunch, everyone. We've got a bit of a special talk, so Steve tells me we've got some tech rock stars, as he said. We have Bunnie, Sean, and Tom, and they're here to tell us about Betrusted, better security through physical partitioning. Please give them a warm welcome.
Thank you. It's nice back to you in Australia again. Thanks for having us here. Just I want to call a little bit to your attention. If you are following along and you're having trouble reading the slides or whatnot, you can go to p.xobs.io/LCA20-BT, and it'll open up in your browser, and the slides will follow along with the talk live. Of course, it doesn't happen if you're watching on the recording, but if you're watching it right now, you can do that. So we are going to talk about a system that is like a device that looks a bit like this that we're coming together. And there's a little bit of a question as to like why would we be going out and reinventing the wheel again. So I'm going to try and motivate the talk a little bit in terms of the background and where we're coming from. So a while ago, I was challenged to give journalists who were behind sort of enemy lines a device they could trust with their life, so that it wouldn't betray the location. And the solution that we had come up with at the time, you can see there's an iPhone, and if you look keenly on the side, there's a flat flex cable coming out that's not part of the normal iPhone. We actually had instrumented all of the radio buses on the inside, and that was fed into a nice 40 FPGA that was running a whole open tool chain, whatever it is, and trying to analyze the traffic patterns to make sure that if your phone was in actual airplane mode, it was actually not transmitting anything at the time. We thought, great, that would be awesome. The problem is that complex things are very hard to analyze. When we thought the thing was inside sort of airplane mode, we would get occasional blips, for example, on the cell phone and the Wi-Fi. Coming out of the iPhone. And before we made a big fuss about it, we kind of looked around and checked around the user agreements and whatnot. It turns out that this is a well-known thing that iPhones do in airplane mode, is that they will sometimes turn on GPS and take a look around. And we didn't have a lot of good explanations for why, but one hypothesis is that they're just looking to build up Apple Maps better, right? And so that's just the thing they'll do, is every now and then is just sort of log your position and send it back. And that would be a non-nefarious thing that we couldn't tease out from potentially nefarious things. So this sort of led me sort of down a path of, okay, well, it's going to be very hard to sort of take these very complex devices and secure them even with an external introspection device of some sort. A second sort of issue is that as we start to use our phones for everything, we have this inherent trust that all the apps stay to themselves and they don't get out of their sandboxes. But the problem is that there's a bunch of vulnerabilities, sort of like Spectre, which is allowing apps to sort of break out of their sort of software boxes and gain access to things that they shouldn't have access to. So a second issue is that software isolation, with sort of the speculative execution and a lot of the timing side channels that are coming to light these days, allows you to pick between either speed or safety, right? You can't sort of have both at the same time in a device because you're going to have timing side channels that can reveal internal state. There's a number of really good papers on this, one particularly by this team at Google that I read, which sort of led me to some conclusion that basically it's going to be very hard to build a general purpose device that you can also trust with high value secrets. A third issue that motivates this is that the adversaries themselves are very motivated. So this here is a recent screen grab of the 0DM payouts, and currently today a zero-click exploit on Android is going for $2.5 million, right? And I don't think that is a sort of measure of how hard it is necessarily to do it, but it's more a measure of the demand for it, right? There's a bunch of people in the world who will pay a lot of money to get access to devices, and there are people who aggregate these exploits and resell them to people who have this money at the end of the day. And so it's not that we are against people who have small resources. They actually have plenty of money. And so when you're talking about people who are looking at spending millions of dollars for exploits, you also have to worry about things like supply chains, right? So attacks where people are bribing couriers to go ahead and swap out things inside boxes. $2.5 million can probably bribe a lot of couriers at the end of the day. Attacks like people have bought hard drives on Amazon, went ahead and put some firmware on the inside and then returned them to Amazon, and now they go ahead and are sold to someone else who happens to be in the same general vicinity that is also for a big corporation. Now they have an exploit loaded onto the hard drive without ever even necessarily having to do anything particularly malicious with the supply chain. They just had to buy something, twiddle with it, put the tamper seals back on, and put it back into the supply chain by returning it. And there are also like the classic known sort of exploits where like the NSA has like literally built devices that go inside a USB cable that can exfiltrate data and these types of problems. So we have untrustable supply chains. And this is finally compounded with the issue that there's no HMAC for hardware. So there's no hash function for hardware that allows us to check that the hardware is what we think it is as easily as a computer binary. So these days we're like, OK, if you pull down a package, make sure the MD5s match, and you're good, right? There's no way I can just give you a hardware device and say, trust me, no one's tampered with this along the way. There's no HMAC for that. There are some devices that are able to do very complicated sort of X-ray level microscopy on these devices, but they literally require building-sized X-ray light sources to do this. So it's not practical. You also have the problem of if once you FedEx it to that facility, the guy FedExing it back to you once again has a chance to tamper with it. So there's no real effective HMAC for hardware, which means that we want to try and solve this problem by moving some piece of hardware closer to the end users that they can verify, that can keep their secrets. The current sort of state of the art for that are things like TPMs, which there's been a number of really good talks about this year already, and then also things like 2FAs, like Sean's worked on the FOMU device, which can serve as one of these devices. And the idea here is that you have a little simple piece of hardware that you can trust to keep a private key or something else on the inside that's going to be tamper evident or tamper proof, and everything should be good, right? The problem there is that it's what I call the I/O problem, is that yes, maybe inside your phone you have a security element that can keep your private keys safe, but the problem is that you're still relying on untrusted input method editors and untrusted screen to go ahead and relay the plain text messages to and from these enclaves, right? So people who have installed an IME on Google, Android may have noticed this little thing that pops up that says this input method may collect everything you type, including your passwords. And a lot of people say, OK, sure. Right? Because what else are you going to do? Not type your passwords at the end of the day? And so this is what I call sort of the I/O problem. And so what it points to is that just developing a piece of open silicon in and of itself doesn't actually move the goalpost minimally forward, because someone will just go ahead and find a way around your little secure enclave to go ahead and acquire your secrets. So the bottom line is that if you want something that's trustable, there are some trade-offs to be made. So I have a picture of two devices here. On the left are AirPods, and on the right is like a headset. They both do ostensibly the same thing. They allow you to talk to people and listen to music. One of them has over 10 million, probably 100 million transistors on the inside, and the other one has probably one, which is used to amplify the microphone, right? So one of them is by far more easy to take apart and verify from first principles, right? But the other one, I don't know, lets you get rid of some wires, I think is its best benefit. Also, it listens to you and it has keyword, attention words and stuff like that, which may be a feature or not a feature depending upon your threat scenario. But at the end of the day, there's a sort of this constant tension between a device that has a lot of features and usability and a thing that we can actually say something about trustably in hardware, because the problem, as I've mentioned before, we have to be able to verify the hardware as close to the end user as possible. Saying this is a complicated device, I'm going to send it to a third-party service to have them check it, then have them send them back to me, once again takes it out of your hands and introduces the time of check, time of use problem for verifying hardware. So if you want to verify, you need something simple. If you want to do something simple, you have to focus on a task. And so the solution that you develop depends upon the context. So are you doing something for mobile? Are you doing something for server? What's your type of user? What is the minimum viable, verifiable product for that particular use case? If you care about security, this is a question I think we have to ask. So we have been working on a project together, the three of us here, which is in a particular design context. So the project's called Betrusted. What we're looking at building is a mobile device. The reason you might want to use it is you might want to talk to someone by text chat or voice. You might want to authenticate, so you want a real 2FA second factor that's not living in the phone that's the same attack surface as the browser you're using to access your website. Or you might want to keep some money in it, like a wallet of some type. The types of people we might imagine using it are what I would call at-risk end users. So this is probably a bit too much for people who just want to say, hi, cat meme type of stuff. But people who are high-value targets, both politically and financially. So when I say high-value, I don't just mean like executives with lots of money. I mean also people who don't have a lot of money but are very inconvenient to people with a lot of money. And also sort of developers and enthusiasts. And also, and this is part of a point that we're sort of gritting our teeth on, we have to be mindful this is a global demographic, not just English-speaking. It's not just English-speaking people who have these sorts of problems. There are people in other countries speaking other languages who are at-risk users. And so this is a kind of a better picture of the device. Actually, this is what it kind of looks. I have a physical sample here if people want to take a look at it. The way to think about this, the problem is it looks a bit like a mobile phone, but it's absolutely not a mobile phone. The way to think about it is a security chip with an input and output surface that you can verify, right? The reason why it looks like a phone is because you need an input and output surface. But on the inside, everything, all the principles going into it are attempting as much as possible to make it very simple and easy for end users to verify. So I would say like a single chip design, and you'll see a number of chips there, of course, but basically all the secure elements, all the security keys, all the secure computations happens within a single hardware attack surface. We're picking an FPGA, and there's another talk I've given which goes into a lot of rationale for why we've done this. And you can check that out. That's from 36C3. And then also, very significantly, we want end user verifiable I/O. So a lot of people say, why not use a virtual keyboard? Well, virtual keyboard requires a touchscreen with a chip that's proprietary that you don't know what's on the inside of it. Physical keyboard is just wires and switches. Like you can just hold up to the light and be like, hey, look, that's a physical keyboard. I see nothing else on it. Black and white LCD. There's basically almost no implants you can hide on that, and you can have some level of trustability to the enclave. But once we sort of commit to living in this simple world, we have constraints. And so the cost to produce versus the amount of RAM you can fit in a chip creates kind of a Goldilocks zone. If we go to an older technology, larger than 90 nanometers, a few megabytes of RAM blows the die size huge, right? So on the right-hand side is, just for scale comparison, 4 megabytes of RAM and a 130 nanometer process might be 70 square millimeters. And for a typical chip company, you would charge an end user price of around $40 for that, right? Which is a lot for a chip that goes inside of a mobile phone. That would not be acceptable. Whereas if we were to go ahead and drive it down to a smaller process size, of course, people know that the best CPUs are made at 7 nanometer. The cost of doing a mass set in that is like $100 million or something like this. We're not, the three of us on the stage, going to find that kind of money to build that sort of stuff. And so there's a certain point at which the cost to make the chips goes too high. Also, we lose options like embedded flash. But at around 40 nanometers, you can put about a few megabytes of memory inside of a chip and still charge a few dollars for it, right? So this actually creates one of the first sort of pillars of the constraints around the software that goes into it, is that you have a few megabytes of memory to live in if you want something that you can verify, right? So this is sort of the design envelope summary. We have application requirements of text chat, voice calling, or voice chat or calling, authenticator, wallet applications. The compute environment is a few hundred megahertz CPU. I think generally logic transistors are plentiful, and I'm not too worried about how much compute we can get. The RAM is the really big problem. It's around a few megabytes. The I/O is going to be a physical keyboard, black and white LCD, and a SPI bridge to an untrusted network coprocessor. So people often ask, what's the network interface? I actually kind of don't care because that's outside of my trust domain. The packets are encrypted already by that point in time. You can connect to whatever network you want through an untrusted coprocessor. And most importantly, the entire thing is verifiable at point of use. You can get this device. There's a set of 6 screws on the front. You can take the bezel off. You can take a look at it. You can compile your own CPU with the own tools on your own device, getting your own random layout into the FPGA. Makes implants a lot harder to pull off. You can check the keyboard. You can check the display, all those sorts of things. So you can actually have a device which you didn't have to send to a third-party service. And you can have some reason to say, I probably can trust what's on the screen. I can probably trust what's going into the keyboard. So, of course, we're at a Linux conference, and I'm going to tell you that Linux is not going to cut it. With a few megabytes of memory, and the idea that we're going through all these machinations to create a verifiable piece of hardware, the next thing I don't want to do is take 25 million lines of code written by 19,000 authors and try to fit it into a device and say, yes, we've solved the security problem, right? I don't think that, first of all, it just won't fit in the hardware. And second of all, I don't think it's going to be possible to audit it. By the time, it's like one of those, like the ship of Theseus. By the time you got from the first plank to the last plank, the ship has rebuilt itself or something like this. So if we went from the first line of code of Linux down to the last line of code of Linux, by the time we finish auditing that, the rest of Linux has been patched and changed, so you're like just auditing it again. So this creates a really big software problem. But the good news is that we have two very talented software people here who tell you about sort of our approach to solving this problem. So Sean, you can talk about that a little more.
So thank you, Bunnie. The operating system we're going to put on Betrusted is called Xous. And now I feel at this point that I have to get up here and justify, why are we reinventing the wheel? There are plenty of other operating systems out there that would be fine. Bunnie has already mentioned, for example, why we don't think Linux is going to be suitable for this particular platform. And just to reiterate some of the Betrusted goals, we have this target to hit less than or equal to 4 megabytes of RAM. Because we want it to be a secure processor, we want to run it in a safe language. And we also want compartmentalization, so we want process isolation, which is not normally a thing you get in these embedded processors, for example, a Cortex M0. And so we've decided that we're going to take a microkernel approach, which allows us to compartmentalize everything from the drivers to the various applications. And we want one of the goals for this to be auditable by a single person. Now I'm going to go into those two requirements at the end. Microkernels have this ability to handle system calls very quickly. This is from a paper in 2010 documenting the amount of cycles and instructions that it takes on x86 64. You could see that even just a simple preread call takes over 12,000 cycles and almost 4,000 instructions. With RISC-V and the microkernel approach that we're taking, a basic overhead without any fancy FPGA hardware thread tricks takes about 66 cycles, which is going to enable us to not pay quite the same penalty for microkernel system calls as we would with a Linux. As for the ability for a single person to audit it, in the wake of Microsoft Windows Vista, they looked at, Microsoft did research into the causes of various bugs within the Linux, the Windows subsystem. And they discovered, and they were looking at all the various, a bunch of different variables from the number of lines of code to the age of the module. And they found that the single biggest predictor for code quality was if one person was responsible for more than 50% of the code in a module, it had a significantly, up to I think 20% better, fewer bugs in a module than one that was created by more than one person. And their definition of module was a DLL, a shared object, a library. So by compartmentalizing things, you get a better code quality, and you reduce the number of bugs. And this kind of dovetails into, we have a friend named Felix who has this rule of thumb, and it goes, the largest amount of security-related code that one person can reliably audit is about 64 kilobytes of binary data. And this is battle-tested, this exists in the real world. And anything more than that, and it just becomes this eldritch kind of Cthulhu monster. You can't actually reason about anything more than about 64 to 128 kilobytes. But so we want to try and keep all of our modules under about this size, which brings us to like the principles of software that we would like to have: safety and concurrency and speed. Do these three principles sound familiar to anyone? These are famously the principles of Rust. These are the three things that they Rust advertises that they provide the holy trifecta: safety, concurrency, and speed. And so we want to actually adopt this language for operating system. So one of the requirements we have is that the actual OS will be written in Rust. Now, because this is a security enclave, we're actually less concerned about speed because we just want to be correct. We don't necessarily want to be fast. Speed is a nice benefit to have, but another benefit that Rust provides us is size. It turns out that LLVM is really good when it comes to optimizing code, and so by using Rust, even the test code that we've got that has a graphics library and some line drawing and some really cool stuff is only a few kilobytes of code. So already we're discovering that this so far seems to be the right choice, both in terms of safety, concurrency, and the resulting binary will help us stay under that 64 kilobyte limit. Now we are writing our own operating system in Rust. There are other operating systems that exist, but the problem is Rust is still evolving, and in order to do an operating system, up until relatively recently, you had to go on the nightly toolchain, which changes relatively frequently. So, for example, a lot of the operating systems haven't been updated or have been started and abandoned because it takes a lot of work to keep up to date with nightly. Stable Rust is fantastic because it won't ever change. Nightly gets you a lot of really cool features, but you have to spend a lot of brain power and time staying up to date with the current state of the art. So as an example, one of the Rust operating systems that is very common, and people have asked me, why don't you use Talk? Talk is fantastic. It's designed primarily for a Cortex M0. It's a very active project. It has some 50 plus users. They actually have a port to a RISC-V CPU, which is what we plan on using in Betrusted. And even more great is they actually have C and Rust user space libraries that makes it very easy to use either language you want to compile down into a program that you could load. It does have a number of shortcomings that make it unsuitable for our project. It currently doesn't have an MMU support. So you can't have separate processes, each with their own memory space. And that's because a lot of the microcontrollers you get for embedded projects, such as the IoT devices that Talk was designed for, just don't have one. And we would like the Betrusted operating system to come with an MMU to enforce process isolation. It also has no runtime spawn support, so any processes that are running when the system comes up will stay running forever. You can't spawn new processes, and this is just kind of a nice thing that we would like to have, being able to switch in between applications in our operating system. Also, just like the message passing system they have is a little bit limited. You can only have one message server per process. But so overall, Talk is just too small for us. Another option is Redox. Redox is fairly famous. It is also an active project. It has a full Rust standard library. It has a full user space. I think they're working on getting support for Redox on real hardware, which is pretty great. Some downsides, though, it's currently x86 64 only, which doesn't really work for us so much. We'd have to port it to RISC-V. It's very much a Unix-like. It has syscalls such as read and write and open that is not necessarily what we want on an embedded device, and it's desktop focused. So the problem with Talk is that it's too small. The problem with Redox is that it's too big. Now, while I was investigating for this talk, I found this operating system called Tifflin. It's an active product, which is good. It has a standard library, which is also good. Then it has a user space. The downsides I saw with it, it requires nightly still, so we'd be on that treadmill. It's mainly x86 64, and more importantly, I didn't really know much about it. There's not a whole lot of documentation on it, which makes it difficult for me as a customer, as a user, as a potential person who would want to embed it, to use it. So you have to tell people about what you want to do. We're not going to start completely from scratch. We're going to have inspirations from other operating systems. Chibi OS is something we've had a lot of experience with for keeping thread sizes really small. Helen OS is a fantastic operating system that is written in C, so we couldn't actually pick that, but it's very much message-based. Solaris has this interesting doors feature where when you pass a message, the receiving process actually inherits the time quantum. And so syscalls become very cheap. And QNX, which is very useful and it's very common in embedded cars, for example, is just a traditional microkernel that has a lot of battle-tested examples of how to use an operating system. But the point is, microkernels, which is what we want to be, just isolate processes and make syscalls cheap. So, having justified what we want to do, I just want to go into a little bit about the systems design that we want to have. In Rust, how many people here have programmed in Rust? Reasonable amount. If you've ever sat next to somebody who's learning how to program in Rust, you will hear many adult words about the Rust borrow checker, because what it does is it prevents you from using memory in a way that would be unsafe. You can't pass something to strcomp and then at the same time pass it to memset 0 and then actually print it out, because that memory might be in use by something else, but Rust enforces this at the language level. We want to have message passing in Xous, this operating system, where you pass pages of memory from one process to another. This is very common in microkernels, but we want to actually adopt this borrow checker such that it works with inter-process borrowing. So for example, in Rust, you have two different borrow types. You have mutable and immutable. Mutable borrows mean one person can take it and modify something and then return it. Immutable borrows can be borrowed by many processes at once. And when you send out a mutable borrow, the person who is borrowing from no longer has access to it. And we will enforce this at the operating system level. When you pass a message, that page is no longer accessible, and if you borrow it, it will crash. Just like in Rust, for example, if you have a reference counted object and it gets mutably borrowed and another code section of code also tries to mutably borrow it, it will panic. The idea behind the Xous message passing model is this will happen at the kernel level, and so we'll get all that nice proven Rust borrow checking actually at the operating system level. So as an example of how this might work, if you have a process that wanted to draw, say, a circle into a frame buffer, the process that contains the frame buffer would pass that frame buffer in a mutable borrow to a graphics library, which would then draw onto it and then return it back to the source process. An example of an immutable borrow might be a font database. So in Xous, we're going to have like the user interface and then the input method editor. Both of those might need the same font, so the font server would do an immutable borrow of that font to both of those processes. But because it's immutably borrowed, if it tried to update the font, that would result in a crash. And as a final thing in Rust, you can actually move memory from one process to another, from one function to another. And we're going to have the same thing in this operating system. For example, if you have a string that you want to encrypt, it might make sense to move that page into the encryption server so that the sending program no longer has access to it. And this is, again, copying the move semantics from Rust. And one of the nice things about a microkernel is that everything is in user space. So this is just an example of what it might look like to allocate an interrupt. Now this is all running in user space, and so you would have a function that first allocates some memory. Let's say, for example, in the system E000 is some GPIO that you want to access. That would get allocated from the system and given to this process. Now because we can't have immutable more than one process accessing the same memory, because just like in Rust, that is a big no-no. If this memory is already allocated by a different process, this would return an error. But if it doesn't return an error, then we can actually claim an interrupt. And again, if interrupt number 2 in this case is taken, and we try to claim it, then that results in an error. But if it isn't, then when this interrupt fires, that's a closure in Rust. This allows us to do drivers entirely in user space, and because it has these memory semantics, memory protection semantics, if a process ends up writing to random areas of memory, it doesn't actually have access to any of that. So I don't know if you've ever written any drivers in the Linux kernel. It's very easy to accidentally overrun a buffer or access memory that you've previously passed to another process, but with this particular arrangement of the system, it becomes much more difficult to do that. It's enforced both by the Rust language and also by the kernel at the message passing level. Now, finally, I want to talk about the features that are missing from this operating system, things that we don't think are going to be good for an embedded secure environment. We're not going to have fork. I don't know if you've ever looked at the man page for fork, but there's all sorts of things that you're not allowed to do when you fork because it gets kind of dicey until you've actually spawned a new process. So in order to avoid that, we're just not going to have fork entirely. I alluded to this earlier. We're not going to have any file system calls. These will be done entirely by a file system server in user space, and they'll be wrapped by a system library. So there's going to be no native syscall number for open, for example. It's going to be a message that you pass to the virtual file system driver. One of the other interesting things that we're going to have is there's going to be no scheduler. The scheduler will be in a user process that claims the timer interrupt, and there's going to be enough hooks in the kernel itself to allow that process to manage other processes. So when you want to call yield, for example, that'll be a message passing. When you want the scheduler to interrupt a process, it calls a function that returns the program counter of the currently executing process. Similarly, there's going to be no threads. Those will be a property that falls out of the scheduler being managed in user space and having access to the program counters. We're going to start with not having locking primitives because in theory the message passing will get us around needing them. Everything that gets called in an interrupt context, of course, interrupts are disabled, so that's where you get the locking from. But overall, we think we can do it without locking. And finally, no shared libraries. This is very similar to what Redox started out with, the Redox operating system in Rust. They're eventually getting shared libraries now, and so this is a thing we could do later on where, for example, you do an immutable borrow of the library you're linking and then patch that in at runtime. We're not going to have them at the start, but that's a thing we can get eventually. So finally, the big thing to remember is that in Xous, the operating system, we're going to have a small kernel, and everything is going to be accomplished with message passing. So by keeping the kernel small, we can hopefully get way below that 64 kilobyte limit. And by message passing, we allow the decoupling of modules so that one person can think about their module and then pass messages to another one. And we're going to have protected memory. So if you do happen to mess up, or if you want to write a server in C for whatever reason, if you do a problem, if you accidentally run off the edge of a buffer, for example, it's not going to affect anything else. So the goal of the Xous operating system is to be understandable by just one human. But of course, you can't do it all yourself. And so Xous is going to be made by many. And here to talk about the operating system is my colleague Tom Marble.
Thanks, Sean. So you heard from Bunnie and Sean about some of the applications that we're going to be targeting for Betrusted. We'd like to be able to support voice chat, voice calling, authentication, possibly a crypto wallet. We mentioned the journalist use case, perhaps taking notes in the field, preparing for a story. And we also mentioned text chat. Text chat is going to be the first application we're going to develop for Betrusted because it covers a lot of the essential building blocks. It covers using the new format of Xous. It encompasses crypto. It encompasses the flow from the keyboard, the input method editor, to rendering fonts and showing things on the screen. So we think that once we have text chat, these other applications will follow more quickly. So when we come to deciding what to do about text chat, we've decided that we're going to initially target the Matrix protocol. Matrix is interesting because it's an open spec, it's an open protocol. There are a number of different secure messaging protocols that we could use. This one we like because there are multiple server implementations, open source, many, many client implementations that are open source, and Matrix will support bridging between, let's say, other networks like IRC or other messaging platforms. So as we begin on this journey to develop apps for Betrusted in Rust, we'll start with text chat on Linux, AMD 64, work on the standard use cases that you would expect from a matrix user point of view, and then begin to look at what the code looks like, the dependencies that we draw in. One of the things that we might do, for example, is we might start with a standard Rust crate that has a lot of ciphers, and we may decide that we're only going to focus on a couple of ciphers and maybe choose some that have been hardened specifically against timing attacks. And then, of course, we're going to do a very rigorous memory analysis to make sure that we're consuming as little memory as possible. And then, as it becomes available, migrate TextChat to Xous running on target on RISC-V. Bunnie mentioned internationalization is really important. We are aiming for Betrusted to work in a global context. So that means not just English, that means European, Latin languages, it means Chinese, and it means even right-to-left languages. And so what that entails is we're going to need to do complex font rendering. What you see here are a couple of examples using font2 and Rust type, using rendering Chinese and Arabic. Below, you may have attended a talk earlier this week from Nate about HarfBuzz. This is HarfBuzz rendering the same Arabic, which does a significantly better job because it's kerned correctly and the direction is actually correct. So outputting things correctly to the screen is challenging, and particularly for in an international environment. Emojis are kind of an interesting thing that we want to support, and if you've ever used Matrix, you know that emojis are used as a convenience way of authenticating your friend. There's enough entropy in 6 emojis to confidently assert that your friend is actually using the same key that you think that they are. And also it's very expressive, so we want to support emojis, so we'll have a means of doing that. That's output. Now for input, we also want to support internationalization, so the Betrusted will have replaceable keyboards. And because it's a hard keyboard, we'll have multiple planes where we can get at different kinds of symbols, and ideally we'll also support dynamic word prediction and correction. So in this way, we can take advantage of the hard keyboard to actually be very efficient and possibly much faster than you might expect with a soft keyboard. Of course, given the use case that Bunnie mentioned, having the input method editor within the secure enclave is really important. So we want to be able to have those all living within the secure enclave. Here's an example of the English QWERTY keyboard for Betrusted. The key layout should be sort of familiar for those of you that are English speakers. It has, you can't quite see it on this rendering, but we have shift keys on the left and right bottom of the keyboard. The keys have different glyphs on the top of them, but we've also worked on other keyboards for other languages. For example, we did some work in creating an AZERTY keyboard, which is for French, and this is sort of a combined, takes the best of the classic AZERTY keyboard and builds in as much as possible from the new AZERTY standard. For example, you can see that we have some of the French-specific characters that are enabled here. I also have a German keyboard. Now, this is the keyboard that's actually in the prototype hardware. Who can tell me what keyboard this is? Dvorak. Very good. So why is the hardware got a Dvorak keyboard? Well, there are 2 reasons. One is that Bunnie likes Dvorak. And the other thing is that by starting with Dvorak, he's making sure that we're not going to forget about internationalization. So we've got some work to do. We're motivated. Now, the next part of the software story is this is a complex hardware and software project, and we're all used to continuous integration when it comes to software, but it's really tricky when it comes to hardware. And so we want to emulate as much of the hardware as possible to debug the design as early in the process as we can. So we thought possibly about using QEMU, and Sean has had some early success in using Renode. So this is a screen capture of running the Betrusted screen all in software, all in Renode. And Sean was able to get the Renode developers to add some extra hooks. Basically, Renode is pretty amazing because we're able to take the hardware, some of the effects from the hardware generation tool chain and create the design files that we need for Renode, add a little bit more of a hardware description, and we can basically simulate the hardware and then, of course, the binaries that are running on top of it. With this, we want to support continuous integration, as I mentioned. So that will be simulating both hardware and software. Ideally, we also want to set up continuous integration to actually run on target devices. And I'm particularly keen on automating UI testing so that we can test fully through the user interface. Some of you may have heard about the reproducible builds project, the idea that we want to be able to create exact artifacts from the same source code. We want to leverage the tools that have been created there. There are a number of things that are tricky about taking on such an ambitious project. Probably the first thing is, as you know, the user experience for secure messaging is really difficult. And if you have some thoughts about how we can do better, how we can make this experience better than, let's say, it is today with the GPG Web of Trust, that would be fabulous. Our text chat application, I'm planning to call MTX CLI. Stay tuned for that. That's very early days. Once we have our continuous integration set up, I hope you'll contribute and take advantage of that and be able to kick the tires and not be afraid to work both in hardware, the operating system, and in application software. And very importantly, it is early days in Betrusted. If you have experience in defending against the threat models that we've discussed, we would really appreciate your feedback because now is the time that we can make course corrections and important changes. And we will ask you to red team with us and analyze the security of Betrusted from top to bottom. I just want to make a quick call out, something I realized from the keynote this morning from Lizzie O'Shea. I didn't realize that because Australia has no Bill of Rights, that the Five Eyes countries would see Australia as a potential testing ground for edgy encryption laws. And I wasn't sure, but I verified with Lizzie after her talk that the All Access Act allows, among other things, communication providers to install malware on a journalist's phone without a warrant. So this use case of possibly installing an input method editor that could steal all your keystrokes is actually a very real use case here in Australia, and I'm thrilled that we're able to come to LCA and share Betrusted with you. So with that, follow us online, betrusted.io. We have all of our hardware and software up on GitHub. We have a channel on in Matrix, #Betrusted. And with that, we're open for questions. Thank you very much.
Please come on and use the microphone.
Hi, I just had a quick one. I noticed you chose Matrix as your communications mechanism. Did you put any thought into whatever the Signal, Open Whisper, is it Signal? Yeah, Signal.
Yeah, actually, we have thought quite seriously about Signal, and I think that it will certainly be possible to support Signal. We'd like to, we don't want to be focused exclusively on Matrix, but I think that looking at what's happened, Matrix is more open to federation and open to having more than one centralized server. So yeah, we definitely thought about Signal, but that's why we chose Matrix first.
Just two hopefully short questions. One, just is the project eventually plans to tape out its own ASICs instead of using FPGAs? And two, for the OS, are you basically rewriting SEL4 in Rust?
I'll take the first one. So are we planning on doing ASICs? I think the fundamental prerequisite for us to do ASICs is that we have to give people a reason to trust an ASIC. So we have to solve the problem of end-user silicon verification first. It's a hard problem. It is a problem we are thinking about and trying to solve, but realistically, it's going to be years and millions of dollars probably to get that program through. And I don't want to necessarily put that in front of getting a device into people at risk's hands. So we're starting with the FPGA. And if we're lucky enough to get funding and the manpower, I have a bunch of ideas to solve the ASIC problem, and I would love to do an ASIC eventually.
Yeah, and for the SCL4 in Rust, that might be what we're doing. But I think even if that is what we're doing, then that is a good thing to have done. I'm not actually sure how much of a microkernel, how much they do message passing. I don't know if it has the Rust-style borrow semantics, which I think are very important for this particular operating system. So I would need to look into more about SCL4 and figure that out. But I don't know that we would actually be able to, for example, get under that 64 kilobyte, one person auditing the whole thing, even though it is formally verified as an operating system. So I don't know.
You mentioned the matrix protocol and an untrusted network processor. Does that mean that you will be implementing a TLS stack or a TCP/IP stack in the device? Do you have some thoughts about where the network layer ends up?
Yeah, can I take that one? Yeah, so the idea is that inside the device itself, it'll have its own sort of layer that runs on top of whatever transport layer you put into it. So we have the end-to-end encryption that happens within the secure enclave. And once the packet is formed outside of that, another untrusted coprocessor can deal with whatever multitude of standards we need to if you're going over Bluetooth or TCP/IP, TLS, whatever it is. We don't want to have to pull in arbitrary standard X with all of its warts into the secure enclave, again, blowing up the code space of things to look at. So basically, the network stack should be all external, primarily for an attack surface issue.
Hi. I don't think I saw it up there. Have you guys had any thought on license?
Sorry?
On what, sorry?
License, software
license. So
start with the hardware level. And then
yeah.
Oh, the license. You said license?
Licensing, yeah.
Yeah. So from the hardware level, we're looking at CERN OHL for the license, and that one's the OHL itself is a work in progress, but so far it's the best fit I've seen to date.
And we're tracking the new version of CERN OHL as well.
Yeah, that's right. There's a new version of it which we're tracking.
So if that becomes available in the right time frame, we might adopt CERN OHL 1.3. Is it?
Yeah, it's a complicated set of licenses.
So that's at the hardware level, operating system level.
Yeah, for the operating system level, currently I've selected Apache 2.0 because that will let us move on to GPL if we want to later, and it gives us more flexibility to go either stay where we are or move in a more copyleft style license.
And at the application level, I think Sean and I may have a little bit of a tug of war. I might pull him a little bit towards copyleft, and it's early days, so I'm kind of leaning left myself. Stay tuned in this space.
Yeah.
Any other questions? Okay. Thank you so much. If you have any other questions, meet us in the hallway after our talk.
Thank you.